Hello students, my name is Shashank Shekhar and today is the ninth lecture of the chapter Alcohols, Phenols and Ethers. So in the previous class we have seen the nomenclature of the ethers and seen its preparation methods. Also we have seen the physical properties, we have seen the illustration regarding some nomenclature. Today we will be seeing this part, that is the physical and chemical properties of ethers. Also we will see uses of some alcohol, so I have left this one to cover it at last. So we will see the uses of two of the specific alcohols, that is methanol and ethanol. So let us start our today's lecture. So these are the topics that we will cover. So first we will see the physical properties of ether. Okay, after that we will move to cleavage of CO bond in ethers, that is the related to chemical properties, and we will see how this mechanism goes in which we cleave the CO bond. Soon we will see the exception of this thing, that we cannot cleave it in case of tertiary group. We have some limitation, we'll see it. So we can do it, but the mechanism changes. Okay, sorry. Yeah, so we can cleave that bond, but the mechanism changes. Also we have a case for any, so we'll see that also. At last we will see some uses of methanol and ethanol, which are alcohols. So they are kind of important in according to their industrial aspect. So we will see to that. Clear? So first of all, the physical properties. So as I have told you earlier in the previous class, and I have shown you the structure also, that ethers do not have a kind of polar bond. Means their bond is of course polar, but their polarity is not that much. Why? Because the same atom is present on either side of the carbon. Of course, the substituents that are further attached to carbon are different, but they do not alter the polarity much. And some polarity develops due to the bond angle, because since they are not in the opposite direction, the direction of the dipole moment is not opposite to each other, so we have some kind of polarity. Clear? So the CO bond in ethers are polar, and thus the ethers have a net dipole moment, although that dipole moment is not that much effective, but they have some. So that weak polarity which we are talking about do not appreciably affect their boiling point. Okay, so if they would have been a strong say dipole moment, then there will be a dipole interaction and we can see a higher boiling point. But due to this low polarity of the bond, there is weak interaction between the dipoles. So here are some examples of these comparison. So we have taken a normal pentane which has a boiling point of 309.1 Kelvin. Then we have 307.6 which has a greater kind of boiling point than your normal pentane. Why is it so? It is due to the weak polarity, or you can say it is due to the polarity. I'm not talking about the weak one, because in pentane there is no polarity, no such polarity. Normal pentane has no such polarity. Clear? So they have some polarity due to which they have a higher boiling point. Okay, sorry for this, I think it is written wrong. Okay, so it will have a higher boiling point. Then we have this butanol, which is polar in nature, of course, because of the OH bond, which is very much polar, because the electronegativity of oxygen and hydrogen is different, and their electronegativity difference is high, due to which there is a polarity in their bond, and you can see the boiling point is also high. So is this clear? Now the large difference in the boiling point of alcohols and ethanol is due to the presence of hydrogen bonding in alcohol. So I have shown this hydrogen bonding in case of alcohol. Okay, so there is a intermolecular hydrogen bonding between different molecules of say alcohol, which leads to this say higher boiling point, plus their dipole interaction, both are present. Next, this alcohols are not that much soluble in water because of the less polarity, again due to the less polarity of your CO bond, as compared to alcohol which has a say high polarity of OH bond. So both ethoxy ethane and butanol are miscible to almost same extent, that is 7.5. so since we have a lower say ether, so they can be soluble. But as we move this or you can say as we increase the size of the alkyl chain, then we will see that polarity will change. Clear? And especially for your say symmetrical ether, this polarity is not that much appreciable. Clear? Respectively, while pentane, so pentane is essentially immiscible with water. So you can see hydrogen bonding between this water, hydrogen, and your oxygen of your ether. So this is the interaction between the hydrogen of your water and your oxygen of the ether, due to which we can see that it has some miscibility in your water. Clear? So this is the physical property of ether. This was about the physical property of ether. Now we will move to chemical properties of ether. So there is only one type of bond to be broken, that is bond between carbon and oxygen. So you take it from either side, it will be the same bond, that is the bond between carbon and oxygen. Clear? So ethers are clearly less reactive than any other functional group, as I have told you, because it has carbon on both sides. The cleavage of CO bond in ethers takes place under drastic condition with excess of hydrogen halides. So we will see the result of this excess amount, okay, in the next say reaction, which we will see now. The reaction of dialkyl ether gives 2 alkyl halides. Okay, so the product that is formed is having 2 alkyl halides. So it is due to the excess of hydrogen halide. We will see the mechanism of it. So how it goes. So first of all, ROR, this is a symmetric example of symmetrical ether, because both of the alkyl group are same on both sides. Now one more thing, they can show metamerism. Okay, ethers can show metamerism. So what is basically metamerism? So I have left this slide, sorry for that. So metamerism means change of alkyl group on either side of oxygen. In case of ether I am talking, right? So how it goes? So suppose you have a ether which is written like this: C2H5 oxygen and C3H, C2 is 6 plus 1 7. Okay, now what do? We transfer one carbon from here to here. It is not a chemical change, I am just changing it structurally to show how does metamerism look like. So it will look like, along with the carbon we have to move hydrogen also to complete this valency. So it will be CH3O C4 to the 819, that is 9 hydrogen. Now you can see that the molecular formula of both of these will be same. Count the number of carbon, it will be 2 plus 3 5, hydrogen will be 7 plus 5 12, and oxygen 1. Here 4 plus 1 5, 9 plus 3 12, and 1 oxygen. Now on both sides we have the same number of carbon, hydrogen, and oxygen, but the structure is different. So if we have different alkyl chain length on the either side of the functional group, then we term that compound can show us metamerism, and these two are metamers of each other. Okay, these two compounds are metamers of each other. Okay, coming back to our cleavage of Ca bond. Clear? So we said that we can form 2 alkyl halides. So how it happens? So first of all, this ROR reacts with HX to give our alkyl halide plus alcohol. We'll look at the mechanism, but just for now follow the pathway. Clear? So we'll get one ROH and one RX. Now the ROH that is formed, that will again react with HX, another mole of HX, as we have taken an excess of hydrogen halide. It will give again RX plus H2O. So if you add both of these reaction, you will get ROR, this and this will be cancelled out, plus H2HX will give us 2RX. So we react 1 mole of ether with 2 mole of hydrogen halides to give 2 moles of alkyl halide. Now this R can be different or same. So if you have suppose 2 different halides, so suppose R dash, then it will give us RX plus R dash OH. This R dash OH will further react with your HX to give R dash X. So two of the alkyl halides will be formed. Now we have HX here. So the order of reactivity for HX goes like this. First is HI, then HBr, and then HCl. So what is the reason behind this? So when you will see the reaction, you will see that the I minus or the Br minus is taking your, say, CH3 plus. They are attacking it. So it is a kind of nucleophilic attack which is much favored by I minus. So the cleavage of ethers takes place with concentrated HI or HBr at high temperature. Now here what takes place is that it depends upon the polarity of the bond. So why it happens, we will see the say this mechanism. We will see this thing in the mechanism. Now let us see our reaction. So we have seen that we take a ether. Okay, what we have taken? We have taken a ether. So we have seen that we have reacted it with the halo acid. So here is our halo acid. So the halo acid that we have taken is Hi. So first of all, this ether will be protonated. Okay, so this ether will be protonated. Clear? Now this is the protonated ether. So this is the first step here. So the reaction takes place with HBr or Hi. So we can take HBr Hi because these reagents are sufficiently acidic. So basically we have to see the acidity of this halo acid. So since this Hi is much more acidic, therefore it will be the most reactive, then the HBr, and then the HCl. So first what happens? It protonates the oxygen atom of the ether. This makes the oxygen more electronegative and hence increase the polarity of the CO bond to facilitate the attack of nucleophile. So why this protonation is occurring? So in the next slide you will see that we will attack a electrophile on this region, nucleophile on this center, that is oxygen containing positive charge. Okay, then the electrophile will donate this electron to make or to compensate this positive charge. Now in the next step, what will happen? Since iodine is a good nucleophile, so first we have protonated it. Now since the oxygen is positively charged, it will attract all the electron density from CH3 towards itself because of the increase in electronegativity of oxygen. Because how does electronegativity increase? Since you have induced increased a positive charge on oxygen, so the attraction for electron of oxygen has increased. Why? Because it has a positive charge, and the tendency to attract electrons is electronegativity. So his electronegativity has also increased. Therefore, this bond has become polar. Its dipole moment has increased. Since its dipole moment has increased, this delta positive has increased. So it will facilitate the attack of your I minus. So what happens? This I minus attacks through SN2 mechanism. So again, SN2 mechanism, we know it very well that SN2 mechanism takes place from that side which is less hindered. Okay, because SN2 is kind of single step and we need space for the nucleophile to attack. So out of these two, this one is less hindered. So I minus attack from the left side, from the methyl side, rather than the ethyl side. And it displaces our this part, that is CH3OH, CH3CH2OH. Now you can see that all of this is taking in a same step or single step through concerted mechanism. The bond is also being formed between I and CH3, plus the bond is also being broken between this carbon and oxygen on both sides. Now ICH3, CH3I bond is formed and CH3CH2OH bond is formed. Okay, so this is the overall reaction. But the difficulty with this mechanism is the reaction is that when primary or secondary alkyl group are present, it is lower alkyl group that forms alkyl halides. So you will see the cause behind it. Basically what happens, so we are seeing that here is our SN2 mechanism. Now suppose on both sides we have secondary or tertiary carbocation. Then in that case, rather than SN2, it will go through SN1. Again, one more thing. What happens next is that we have seen that both of the alcohol and the ether are being converted to your alkyl halide, but we are left with alcohol. Now one more step will take place. So since we have said that we have taken Hi in excess initially, clear, we were taking Hi in excess initially. So the reaction is carried out at high temperature and ethanol reacts with the ethanol that we have formed. It reacts with another molecule of Hi and convert into ethyl iodide. How it happens? Let us see. So here is the mechanism. So we got this species initially and now it reacts with Hi. How does it react? So we know that this Hi is a strong acid and it can be protonated. This CH3COH, CH3CH2OH has one oxygen with a lone pair. So this lone pair attacks the H and leaves us with I minus plus this one. Now this is a very good leaving group. This is a good leaving group. Again, our I minus that had been kicked out, this attacks from the back and gives our CH3, CH2I. Now this mechanism also, this substitution mechanism also goes through SN2 mechanism. Clear? Now in the last step, what happens? Alcohol is converted to alkyl halide. So both of the alkyl group that is present on the either side of our ether are converted into alkyl halide. Now you can see that this mechanism is quite similar to our ether one. In that also we have our I minus which attacks from back side, but the difference is only that we have now H in place of R. So therefore, since this bond polarity is increased much more, because H2O is a much more better leaving group than ROH. Okay, H2O is a much better leaving group than ROH. So this reaction goes faster because of the greater polarity of the bond due to the presence of H in place of R. Okay, overall mechanism will look similar to you. So what I am saying is that the overall mechanism will look similar to you. The only difference is that in this case, that the leaving group is good first of all, and the polarity of the bond has increased, due to which the attack can be facilitated much easier, because the R that was initially present here was somewhat satisfying the valency of this O plus. So let me show you here. Okay, so this is important, that the rate of reaction only depends upon the first part where the I minus has attacked. But in this case, since we know that, okay, so this happens CH3 CHO CH3. Suppose we have CH3 here and we have H, and I minus was attacking from the back side. And in the second case where we have the alcohol, it looks like this. Now this H does not show plus I effect, but this carbon shows this plus I effect, due to which this positive charge that has been formed here due to the protonation of oxygen has been say counterbalanced. Clear? Now since it is counterbalanced to some extent, I would not say it is completely counterbalanced, it is counterbalanced, or you can say neutralized to some extent, due to which the bond polarity between carbon and oxygen will decrease. How? Now the oxygen electronegativity has not increased that much as it would have been increased due to the oxygen alone or due to the OH bond, because H is not showing an active effect. Therefore, this CH3 CH2 electrons will not be getting attracted to that much extent as compared to this. So the attack of this, say, nucleophile is also not that much facilitated. Where in this case, we have H, so the positive charge is not that much compensated. Therefore, electrons are much more attracted from this side, and the I minus attack is facilitated, or the positive charge has been increased. Okay, clear? So I cannot take this one because in case of secondary or primary, the case changes. So we'll see how it does not go through SN2. So I will show you through this only. Okay. Yeah. Now, okay. So this is the thing. So therefore, the reaction rate, if I say it as K1, it has K2, then K1 will be greater than K2. Next thing. So this was about the mechanism of the cleavage of CO bond. Now we have some exceptions. We will look into it. So in case of secondary and tertiary, we have exceptions. And in case of your, say, phenylic ring, we will also see. So in the case which our ether oxygen is directly attached to phenyl ring, we have a difference in the mechanism and also in the product. Clear? Now next, exception of tertiary group. So what we do, we take an ether here that is having a tertiary carbocation. How? This one is primary. Okay, no problem. Okay, this is having no problem. But it is tertiary. You can see that this is tertiary. So what happens now? So if we have a secondary, or sorry, if we have a tertiary carbocation available, tertiary carbocation, only if tertiary carbocation is available, then it will not go through SN2 mechanism, it will go through SN1 mechanism. What I am saying is that, so let me get a clear idea of it. Suppose we have three cases, CH3O, CH3, both are primary. Second is CH3, CH2, O, CH3. Clear? CH3, CH2, CH2, CH3. And the third one is okay. So this is the thing. This one goes through SN1 mechanism. This one goes through SN1 mechanism. Attack takes place from here. But this one does not go through SN1 mechanism. It goes through, sorry. This one goes through SN2, and this goes through SN1. And this thing, so it has the option, it can go through SN2 also from this side and SN1 also from this side. But it takes not this one, instead it takes this one. Clear? So this is the thing I am trying to tell here. So here we have our CH tertiary carbon here. So as it is attached to 1, 2, 3, so it is a 3-degree carbon. Therefore, it will go through SN1 mechanism. You can see very clearly that our I is attached to this carbon rather than this one initially. So it is because in step 2, you can see that in the step 2, the reaction goes like this. So step 1 is similar. First occurs the protonation of our ether. But in the step 2, what happens is this breaking of bond takes place. This goes here. This goes here, and we are left with a tertiary carbocation. Now, what is the thing in tertiary carbocation? If you remember, tertiary carbocation is the most stable one of all of these. Then the secondary and primary. So if we compare it with the secondary and primary, then it is more stable. I'm not talking about diallylic carbocation or the phenolic carbocation, benzylic carbocation. I'm just talking about our primary, secondary, and tertiary. So tertiary carbocation is more stable than our primary or secondary. Due to this reason, it facilitates our SN1 mechanism. So first this bond cleaves and we get our tertiary carbocation. How it is stabilized? Two factors were there. So if you remember, we have plus I effect from the CH3, and we have our hyperconjugation that is coming from alpha hydrogen of the methyl group. Okay. So what was alpha hyperconjugation? It was basically the donation of sigma electrons from carbon hydrogen bond, pi sigma bond, to the anti-bonding of the carbon that is having a positive charge. Okay, so it is because in step 2 of the reaction, the departure of the leaving group CH3OH takes place. So this group depart first. Okay, so this group depart first. So what does it do? It creates a more stable carbocation. Now we have a I minus, because initially we have protonated this with the help of H. So I minus, we are left with I minus. Now we have a carbocation and a nucleophile. So this one will attack here and we will get our alkyl halide. So this reaction follows, in case of this substrate only, it follows our SN1 mechanism if we have a tertiary carbocation, or we have secondary or both sides then also. Now next is this one. So as I have told, we have a different case for anisole. So what is the different case? So in case of anisole, one of the, suppose we have taken anisole, it is R, suppose is CH3 here. Okay. So if we do the HS reaction with this anisole, you will see that you got your RX, that is in this case is CH3X. But this will not give further reaction. Okay, this will not give further reaction. Now you should think about this, how it would have been happened. Okay, how it would have been happened. So basically what we are doing in this reaction, all of this reaction, we are doing nucleophilic substitution either through SN1 or SN2. So if you remember about your previous classes, you must have seen that nucleophilic substitution, it's not possible for phenol. It is sometimes possible, but in drastic condition or in special substrates also only. So this species, that is the phenol, it does not facilitate any nucleophilic attack with our HX. So what do we mean here? That the bond between the CH3O is weaker than the bond that is between OC6H5. So we have a bond between CH3 and O, and we have a bond between C6H5 and O, or the carbon of C6H5 and O. But this bond has a partial double bond character. How? So it has lone pair, it must have donated it. that would result in this kind of resonating structure. Okay, so you can see that we have a double bond character between carbon and oxygen. Therefore, this bond is very difficult to break by the attack of I minus. So due to this reason, phenol do not further goes your nucleophilic substitution to form your say your alkyl halide. Okay, this is due to the sp2 hybridization of the carbon group of the phenol group. So if I put all of this in a nutshell, I would say that okay, we have a reaction that in which we were reacting our ether with a halogen acid. Now the order of reactivity was going like this: Hi, HBr, HCl. Now one more thing, if we have a say primary carbocation on the either side, then we will take the mechanism according to SN2. If we have secondary or tertiary carbocation on the both sides, then we can say that it will go through SN1 mechanism. Okay, and if we have tertiary carbocation, just tertiary carbocation and our primary carbocation, then also the reaction will go through the SN1. Means the SN1 is being more preferred here. Only in case of primary carbocation where tertiary is not present, then and then only it will go through SN1 mechanism. Okay, so this was about the say our reaction of your with halo acids. Then we have the special case of tertiary. Okay, sorry. Then we have the special case of anisole. So this is the special case where we saw that okay, we are getting one alkyl halide from one of the R, which was not phenyl, but the other one, which is phenyl, it is not giving your alkyl halide due to its resistance towards your nucleophilic substitution because of the carbon oxygen double bond. Okay, so this is the about the cleavage of CO bond. Now we will move to some commercial alcohols that are used in day-to-day life. So we will talk specifically about the methanol and ethanol. Now you will notice one thing, that all of these methods that I will show you right now will not be according to laboratory. Okay, so they are not laboratory method. Instead, they're industrial method, because we need to produce a large amount of this methanol and ethanol in case of industry. But it cannot be done with our primitive method like our dehydrogenation or your say any other reaction, or your say we are just hydrogenating our alkene. We cannot do it so. So for that we use special type of reaction which have special type of catalyst, of course, to facilitate that reaction on a larger scale. So as I told you that we will see only two types of alcohol preparation, that are methanol and ethanol. So let us first see about methanol. Okay, so let us see our methanol here. Okay, let us see the methanol first of all. Now we know that methanol is also sometimes termed as wood spirit. Okay, so it is sometimes termed as wood spirit, and it was produced by destructive distillation of wood. So for this reason it is called as wood spirit. Now how is this produced on an industrial scale? So today most of the methanol is produced by catalytic hydrogenation of carbon monoxide. I would tell a more interesting fact here, that today's methods of preparation of different organic compounds are not done with the help of simple organic synthesis. Okay, they are not done with the help of simple organic synthesis, because the introduction of metals have drastically changed the methods of preparation of various organic materials because of the greater efficiency. Okay, because what is happening, they are producing the required product with only a small amount of catalyst first of all, and they are not harming the environment to that extent. I would not say that much it is not that much good, of course, but as compared to organic synthesis, which results in a greater wastage and all, because their yield was not high and the process was also slow, compared to that, this metal based organic chemistry is much more efficient. First of all, their efficiency is high, a greater amount of product you will see, and second, there is not that much time consumption also. Okay, so it occurs at a very fast speed. Clear? We will not see or encounter the metal inclusion, you will see some reactions, but their mechanism will be obvious. Okay, like our catalytic hydrogenation, in which we use palladium or platinum. So that is the example of that. Okay, so similarly, we use this methanol by catalytic hydrogenation of carbon monoxide at high pressure and temperature, and in the presence of this catalyst, that is ZnO and Cr2O3. Okay, so we take our carbon monoxide and hydrogen, and at high pressure and high temperature, we perform this thing in the presence of catalyst to get our CH3OH. Okay, so this is one of the mechanism. Now, if I talk about the methanol physical appearance, so it is a colorless liquid which boils at 337 Kelvin. So if you compare it with water, which is 273 plus 100, that is 373 Kelvin. So it is less. And how much less? So let us subtract it. So 373 minus 337, 13 minus 7, 6, 5 minus 3, 2, 4 minus 3, 1. Sorry, it is 3. Okay, yeah. 6 minus 5 minus 3, 2. It is less than 26 degrees Celsius. So this is a large difference. Okay. If you just convert it into Celsius, you will get as 273 minus this, 13 minus 7, 6. Okay, sorry, 337 minus 237. Then you will get 7 minus 7, 0, 3 minus 3, 0, 3 minus 2, 1. Okay, 273. Sorry for the confusion. 13 minus 7, 6. Okay, so this is 64 degrees Celsius. So it is not that much high, and I have told you the reasons are obvious, because this H2O can form the hydrogen bonding from both of the hydrogens, okay, due to which reason it has a higher boiling point as compared to the alcohols, because alcohols are quite, you can say they are volatile in nature, very much volatile in nature as compared to your simple water and all. So if you keep methanol and ethanol in open, they will disappear in a day, I would say in a half day also. Okay, so it is highly poisonous. First of all, it is highly poisonous in nature. Ingestion of a small quantity would result in blindness, and large quantity can even result to death. So methanol is used in solvents in paints, varnishes, and chiefly for making formaldehyde. So we can convert this thing into formaldehyde. So think about it, that how you can convert this thing into formaldehyde. I'm asking about the organic synthesis. So what are we doing? We are converting our CH3OH into formaldehyde. The formula of formaldehyde is HCHO. So what we are doing, we are just oxidizing it. Now, since it is a primary alcohol, we cannot use a very strong reducing agent, or it will be converted directly into our carboxylic acid. So we will use PCC for that. Okay, so you can you must try these things, okay, by your own, that how we can convert one functional form into another. That would be very helpful for you. Next is our ethanol. So ethanol was previously produced by fermentation. So you must have seen this or observed this thing, fermentation. Basically, it is a kind of very old method or primitive method that is used for the preparation of ethanol, and it is the oldest method from sugar. So it was prepared from sugar. The sugar in molasses. So molasses is kind of eatable only. You can use it for. So it is a sweet taste thing. Okay, this molasses. So the sugar that is present in molasses, in sugar cane and fruits such as grapes especially, is converted to glucose and fructose, both of which have the formula C6H12O6 in the presence of enzyme. So first, what do? We convert this ethanol into glucose and fructose, and which we convert this sugar into glucose and fructose, which have the formula C6H12O6, and the enzyme that we use is invertase. and this glucose and fructose undergoes fermentation in the presence of another enzyme that is called gymase to give our ethanol plus CO2 gas. Now this gymase is found in yeast. Okay, this yeast is a kind of microorganism, single cellular microorganism. So it has zymase, which it has zymase. This zymase is basically used by the yeast to convert its sugar that it has intaken into your energy, plus this CO2 gas is released by the yeast. Clear? So we use this gymase to convert our C6H12O6, that is our glucose and fructose, into alcohol and 2CO2. If you ask about its mechanism, then it will be very complicated. You cannot imagine the complex mechanism that is behind this kind of, say, our enzymes. So what I want to make the point here is that in the organic synthesis, you may imagine the say mechanism to some extent by, say, our any trapping methodology like our spectroscopic methodology or isotopic methodology. You can use all those and trap them intermediate and get a mechanism or get an idea of mechanism. But when I talk about this complex catalyst like invertase, zymase, their mechanism is very complex. Okay, you cannot just simply do it. They are involved with metal and all, and they do it on a very efficient way. Okay, although their temperature and amount is very specific, you cannot take any temperature or any amount, it will not work, but it will act very efficiently if you are able to isolate this enzyme. So in wine making, grapes are the source of sugar and yeast. So the wine which you have heard, okay, so wine that is prepared, so in that also we convert our sugar to this alcohol by fermentation, but the sugar that is being used are used from the grapes, and this yeast is slowly you can say built upon this grape. So what they do is they keep it in a place where they start to rot and yeast start to develop, and this yeast that has been developed, they slowly convert the sugar present in grapes to your alcohol. So it is kind of rotting of the grapes. So as grapes ripen, the quantity of sugar increases and the yeast grows on the outer skin. So you know that as the fruits ripen, their sugar quantity increase, and with time yeast grows on their skin. So when these grapes are crushed, the sugar and the enzyme come in contact. So sugar is present inside your grapes, and on the skin the yeast is formed. So when we crush it, the sugar and enzyme come in contact and the fermentation starts. What happened? Fermentation starts. The fermentation takes place in anaerobic condition, that is in the absence of air. So in that case, carbon dioxide is released during fermentation. The action of gymase is inhibited once the percentage of alcohol formed exceeds 14%. So why is it so? Because it is simply due to the Le-Chatelier principle, that it can only form product up to a certain extent. After that, we have to remove our, say, alcohol or isolate our alcohol to get pure alcohol. But after 14%, it does not happen. So if air gets into fermentation mixture, so what happens? Why do we do it in absence of oxygen? So if air gets into our mixture, the oxygen of air oxidizes the ethanol to ethanoic acid. So what happens is that ethanol is oxidized into ethanoic acid, which in turn destroy the taste of the alcoholic drinks. It would make it sour. Okay, so nowadays large quantity of ethanol are obtained by the hydration of ethene. So this is another method. So where we use the ethene and do its hydrogenation to get our ethanol. So these are the two methods. Okay. So I would suggest you to learn to try to remember all these important reactions, because in a first look they would not look important, but they are very important. Exams questions are directly asked about the, say, catalyst that can be deployed here, zymase or invertase and all of those. Okay, so industrial methods are important. So we saw two. First was methanol and the second one was ethanol. So methanol was basically prepared by the reaction of your, say, CO2, you can say hydration of CO2 to convert it into your methanol, that is CH2OH. Okay. Now, next we studied about ethanol, in which we use the sugar of, say, molasses or sugar cane or fruit, and interact it with the invertase to interact it with the zymase to convert it into alcohol and carbon dioxide. And one more thing, that is an important reaction, that why do we do not expose it to the air, or why do we do it in the absence of air? Because as it interacts with this air oxidizes our ethanol and converts it into ethanoic acid and makes our wine destroys our wine, make it sour. And this is very important, that ethanol that are obtained today or that are used today are mostly done using our ethene. Clear? So this was for today's class. We studied about the physical properties of ether and seen how this boiling point and all this say miscibility of ethers, which was due to the hydrogen bonding in case of our solubility, and dipole interaction. Although dipole is weak, but there is interaction. So dipole interaction between different molecule of ethers. Okay. Then we saw our cleavage of CO bond in ethers. Also we saw our mechanism, and we saw different cases where we have tertiary, secondary, where we can do SN1 and SN2. And then we have see the anisole case, in which the phenol was not further changed to alkyl halide because of the strong bond character between oxygen and carbon. At last, we see our commercial product like methanol, ethanol, that are say produced on a large scale for industrial uses. Clear? So with this, I would end my lecture. Thank you.